Okay, so to go on discussing this problem of entanglement, I would like to describe in the next 2 or 3 slides what is a 2-bit quantum gate. It's a device which couples 2 qubits. One qubit is called the control, the other one is called the target. And the idea is that the state of the control determines what happens to the target qubit. And I have represented this here, this kind of sketch. You see here in red, the upper line describes the evolution of the control. This is the state of the system at the input. The target is here in blue, this is this line. And you see what happens will be expressed by what I call the conditional dynamics. What is this conditional dynamics? If the control is in state 0, nothing happens to the target. But if the control is in state 1, the target undergoes a unitary evolution, which I have called U target. And another important point is that the state of the control does not change. If it's 0, it remains 0. If it's 1, it remains 1. So the control is unchanged, but it determines how the target will evolve. So if the control is in state 0, nothing happens. And if the control is in state 1, the target undergoes the transformation U target. You see immediately, due to the non-linearity of quantum physics, due to the linearity of quantum physics, superposition principle, you see immediately that this gate produces entanglement. Suppose that you start with the control in the superposition of 0 and 1. You see this part, the state 0 will do nothing on the target, but if you are in this part of the wave function, then the target will be affected and you end up with an entangled state. So you see that it creates entanglement. Yes, of course.
Like if there's some there's some electrons
that
are orbiting with the planetary nucleus, and there's some force that let them orbit. But the force is carried by bosons.
Yes.
And they have like a spin of a state. And so if they are interacting all the time, but so you can just measure some pure state because they are interacting all the time.
Yes, but you have a pure state for the global system, but you cannot separate the parts. Of course, the global system remains always in a pure state. What I have discussed is that if you have a system made of 2 parts, and if you consider only one, then to describe this part, you have to assume that describe it as a mixture. It's the same if you take an electron and a proton. The atom is just an entangled state. You have eigenstate for the system, but if you look only at one system, then you have to trace over the other one, and you get a mixture also. So here, so you see that if you start with a superposition for the control, you get an entangled state in the end. And now you can also see that if you go in the opposite direction, since U it is a unitary reversible operator, if you start with an entangled state, the gate can disentangle and give you, in the end, 2 separate systems. So the gates are devices which allow you to couple and decouple qubits. And in fact, when one is thinking about building a quantum computer would be a device which is made of a huge number of gates, which will entangle a large number of bits. And in some cases, this will accelerate calculation and operation. But it's just, for the time being, it's just a theoretical object. It's very difficult to realize. On this slide, I describe a special kind of 2-qubit gate, which is called the control NOT gate. So it's a gate which realizes the operation sigma x on the target. What is sigma x? I remind you that sigma x is a density operator with off-diagonal elements. Sigma x flips the spin. If the spin is in state plus, it becomes minus. If it is minus, it becomes plus. So this is a conditional dynamics, which says if the control is in state 0, nothing happens to the target. If the control is in 1, it flips the target from one state to the other. And this is what I have written here. This is called the truth table. You see 0, 0 gives 0, 0, 0, 1 gives 0, 1, but 1, 0 gives 1, 1, and 1, 1 gives 1, 0. And this gate is interesting because it realizes the addition modulo 2. You see that if you call A, this I called A control 0 or 1 and A target 0 and 1. If you start with A control, A target, you get A control plus A target. 0 will not change, but if you are in 1, you get 1 plus 0 gives 0. 1 plus 0 gives 1, 1, so you add the 2. And if you have two 1s, 1, 1 gives back 0 because you're in basis 2. So this is why this gate is interesting, because it's a typical gate which is used in all computers, except that here you have a gate which entangles the qubits, which is of course not the case in a classical computer. So since I want to spend more time on non-locality, I will not discuss that more. Again, this gate produces entanglement, of course, and in reverse operation, the control gate can disentangle two qubits, and this is clear here. On the next slide, I just describe how you can realize this kind of gate. So I give you the Hamiltonian, which realizes this gate. So this Hamiltonian is very simple. It's the product of 1 minus sigma z for the control times 1 minus sigma x for the target. So I won't discuss that, but you have all the elements to do the calculation. I just show here that the effect of this Hamiltonian on the state is given by this. So you have, in fact, you have 3 states which correspond to the eigenvalue 0 and 1 state which corresponds to the eigenvalue different from 0. And so you can complete the evolution and you find that at some time, this gate will give exactly what we want. That is 0, 0 gives 0, 0, 0, 1 gives 0, 1, 1, 0 gives 1, 1, and 1, 1 gives 1, 0. So I let you do that as an exercise. And I would like to spend now the rest of the lecture on the concept of non-locality. The fact that entanglement gives rise to very strange, very counterintuitive features if you consider an entangled system made of 2 parts which are very far from each other, and you start to perform measurements on the 2 parts. And this discussion has started a long time ago in 1935 with a famous paper by Einstein and his colleagues Podolsky and Rosen. So it's called the EPR paper, in which they discuss a situation of entanglement which led them to consider that quantum physics could not be complete. And we'll discuss this now. So what was the problem that Einstein, Podolsky, and Rosen discussed? They considered 2 particles, for example, an electron and a positron, 2 particles which are in an entangled state, very simple in principle, an entangled state which is described by the equation that I have shown here. You see, if the first particle has momentum p, it's a one-dimension problem, so it's very simple. If one particle has momentum p, the other one has a momentum minus p. So the 2 particles go with the same velocity in opposite direction. But we don't know what is this common velocity, this common momentum. So you have a superposition of all possible p values, and you take the superposition of all these states. So this is a highly entangled state. And you know that if you measure one and find the momentum p, you will find momentum minus p for the other. Now, there is a slight complication here, which is very important. You add a phase here. For p, you had an exponential e minus I p r naught over h bar. R0 is a parameter. It's a length, distance, and you just add this factor. Why is it important? What does it mean? It means that if you compute, for instance, if you compute the wave function of the global system, xa, xb, psi 0, you will have to multiply by the bra xa times p and by the ket the bra xb times minus p. And xap gives you eip xa, xb minus p gives you minus ep xb, and you have this phase factor minus R0. And you see that the phase that you have here is such that when you integrate over p, you get just a delta of xa minus xb minus R0. This is a property of Fourier transform. If you have all the p's, it means that your function is flat, and its Fourier transform will give you a delta function. So you see that if you put this parameter R0, what you have built is a very special wave function. The two particles have opposite momenta, and the difference of their position, this is their distance, is R0. So you have two particles which are strongly correlated with each other. They have opposite momenta, and they have a distance separation which is fixed. So for all, what you have is PA plus PD is equal to 0, and XA minus XB, which is equal to R0. So this is the kind of correlation that you have at a given time. Of course, I have not written any time evolution, so it's why. So this is what happens at the given times, which I call t equals 0. So what does it mean? First of all, it understands that you can measure with precision. You have an infinite precision on PA plus PB and XA minus XB. It means that you can measure simultaneously the sum of the momenta and the difference of the positions. So this means that the sum of the momenta and the difference of the position should commute. And indeed, it is the case. I let you do as an exercise to compute XA minus XB commutation with PA plus PB, and you find 0. Because XAPA gives IH bar and minus XBPB gives minus IH bar, so you find 0. So you see that there is no contradiction in quantum physics. You can measure the sum of the PA and find 0, which means that the PA are opposite. And you can measure the difference of the XA and find R0, which is a constant because you have this commutation. So Einstein and Podolsky and Rosen looked at that, and they found it very strange. And this is what, in fact, this is one of the rare papers, theoretical paper, which got a front page article in the New York Times in 1935, because Einstein was involved. And you see, Einstein attacks quantum theory. Scientists and two colleagues, the two colleagues are not named, find that quantum physics is not complete, even though correct. So you see, Einstein understood very well how quantum physics was working. He did not contest that it was useful to compute a lot of things, but he said, in this case, for this kind of thought experiment situation, I find that the result cannot be right. So what was not right in Einstein's mind? What Einstein said is the following: and assume that you have two observers which are located at two faraway positions. And as usual, we call one Alice and the other Bob. So Einstein did not use this kind of denomination. And Alice sees a particle, receive one of the two particles, and she wants to know what is the momentum of her particle, what is the position of her particle. And Einstein said she does not have to make the measurement. She just has to ask Bob. If Bob finds P, she will know that she has minus P. If Bob finds X1, she will know that she has X1 minus plus R0 because of this relation. So he says, this is very strange because Alice does not have to look, and she knows what the result will be, and it's a result which is random. And so he said, this looks like something else, which is very classical. Assume that there is a third party, a third guy who puts takes two particles, two balls, two cubes. One is painted in red, the other in blue. He sends the red to Alice and the blue to Bob. Alice does not have to open her envelope to know her color because she just has to ask Bob. If Bob finds red, she knows that she has blue. And if Bob finds blue, she knows that she has red. So the situation seems to be quite easy to understand if you make this kind of classical analogy. Now the situation is more complicated because there are two parameters you can measure, P and the position, and we know that you cannot measure on the same particle P and X, because if you measure P, you change X. And so you have to imagine a classical experiment which is a little bit more complicated. But what you can imagine, for instance, is that you have two balls. One is painted in blue, the other in red, and they are slightly different sizes. One is a little bit smaller than the other. To find the size, you have to touch them in the dark. And if you touch them, you will erase the paint because the paint is very fragile on the surface. So you can find which one is big and which one is small, but you will not have the color. On the other hand, if you want to have the color, you have to put some light and then the ball explodes. So you will find the color, but you will not be able to find whether it is small or big. So you can imagine a situation in which you can measure only one of the two parameters, the color and the size. So it's exactly what we have here. Alice can either measure the position by asking Bob to do it, or get the color by asking Bob to do it. So, but in any case, Einstein said, if this happens, it means that the information about P and X should have been in the particles while they're propagated. It should be what he called an element of reality, which should have existed before you look. Because otherwise, it's very strange. It means, according to Bohr, it was not the case. Bohr says it makes no sense to talk about the position of the momentum before you measure it. The result is produced randomly by the experiment, depending upon what kind of experiment you do. But Einstein said, I cannot understand that because it happens at a very large distance, instantaneously. It's something which is not possible. It should have been an element of reality. Something should have propagated between the two for this kind of correlation to happen. And so he assumed that there were some hidden variables which were not taken into account by quantum physics, by the formalism of quantum physics, which explains this kind of correlations. And so he concluded by saying quantum physics might be correct to describe phenomena, but it's certainly incomplete. So, and this remained at this point because the experiment this experiment of Einstein, Podolsky, and Rosen is impossible to perform. They did not describe any apparatus which prepares this state, and there is no way to understand how the experiment could be done. There is another flaw in this, is the fact that this perfect correlation between P and X is valid only at time t equals 0. If you go at a different time, the wave function has a phase factor, which is E minus I Hamiltonian T over H bar, that is E minus I P square over MH bar. And this phase factor destroys the perfect correlation between P and X. So if you have to do the experiment just at one time, it's absolutely impossible. It's very difficult. And so the problem exists because what Einstein said cannot be contested, but you cannot do an experiment like that. And so the situation evolved until the 1950s, when Bohm had an idea to rephrase this, but not with a continuous variable position and momentum, but with spin variables. He imagines that you prepare a pair of spins and make measurements on the two spins at a large distance. And you can rephrase the argument of Einstein, that's what I will do now, and imagine an experiment which would try to see if there are hidden variables or not. And this is what the work of John Bell, beginning of the 1960s, in 1964, Bell took at its face value the argument of Einstein. There are hidden variables. The value of the spins are predetermined when the particle interacted, and we just have to find out what they are. And by assuming this, he was able to establish an inequality which had to be respected by correlation of measurements performed by Alice and Bob, and quantum mechanics violates these inequalities. And so this is what I want to discuss now. And this violation of the Bell's inequality is a demonstration of the fact that there cannot be hidden variables, and that Bohr, in spite of all the strangeness of quantum physics, Bohr was right. So let's discuss that. Let's start with one of the Bell states. I could take any Bell state, but I've chosen to take this Bell state, which is 0, 0, plus 1, 1. So you have two spins, which are in this highly entangled state. And the question I ask is, if I measure the two spins, what kind of result will I get? First of all, if I measure them along the quantization axis, which I call Z, it's clear that if I find plus for the first one, I will find plus for the second one, because it will be the 0, 0 part. And if I find -1 for the first, I will have -1 for the second one, because this will collapse to the part 1, 1. So you see that the product of the two spins along Z gives always +1. So this state is an eigenstate of the product of the two spins along the Z direction with the eigenvalue +1. Okay. Now the next step is that I will now generalize this and tell you that if I, instead of measuring on this state sigma Z, I measure any common direction at any direction different in the X or Z plane. I decide to measure sigma U and sigma U for A and B along a direction which make an angle theta with the Z axis in the Z or X plane. So what is the observable that I am measuring now? I am measuring the quantity which is sigma ZU for the particle A and sigma ZU for the particle B. And this is obviously cosine square theta sigma ZA sigma ZB plus sine square theta sigma XA sigma XB plus the cross product sine theta cosine theta sigma XA sigma ZB plus sigma ZA sigma XB. I just made the product of sigma Z cosine theta plus sigma X sine theta for the two particles. Okay, so this is what I am measuring. And now let's have this operator acting on this state. What you can find is that here you have cosine square theta acting sigma Z1, sigma Z2 will give you exactly the same state, because sigma Z acting on this and this will give you +1, and this time you have 2 times -1, which gives +1 again. And again, this state, which is sigma X, will flip 0, 0 into 0, 1, 1, and back the other one. So you get the same thing here. And cosine square theta plus sine square theta gives 1. So the first two, the action of the first two parts of this sum leaves the state psi plus invariant. And the last one gives 0. Let me show that. So in fact, I have shown that sigma Z1, ZA, sigma ZB acting on this state gives the same state. In other words, psi plus is an eigenstate with eigenvalue +1 of this operator. So what does it mean? It means that in the basis along the U axis, we have again the same correlation 0, 0, and 1, 1. If I get the first spin 0, the second has to be 0, because I must find 1 when I multiply the two Z value. And if the first one is 1, the second one has to be 1, because I have to multiply -1 twice to get +1. So you see that this correlation, this state can be written in the same way, the same expression along Z or along any U direction in the X or Z plane. So you have a perfect correlation if you measure in any direction between the results that Alice and Bob will find if you send one particle to Alice and the other to Bob. So this means that you can take the same Einstein's argument again. Alice does not have to measure in the U direction. She asks Bob to measure. Bob finds plus, she will find plus. If Bob finds the other direction, she will find the other direction. So again, the value of the spin in any direction should be an element of reality. It means that it should be a hidden variable which is pre-existing any measurement in the two particles. So up to now, we are just followed Einstein's argument. And then this is a point where Bell is coming into the game. Bell is saying the following thing. Okay, we have these two entangled particles in this state. Alice makes some measurements, Bob makes some measurements, and we complete the game in the following way. Alice will measure in two different directions, arbitrary different directions, which I will call A and A prime. She will either measure the spin along A or the spin along A prime. Bob will do the same. He will take two directions, B and B prime, and he will measure the spin either along B or along B prime. And for each pair of spin, Alice will make one of two measurements, Bob will make out of it two measurements. We'll call epsilon A or epsilon A prime the result of the measurement by Alice, and epsilon B or epsilon B prime the result of the measurement by Bob. Epsilon A and epsilon A prime are equal to plus or minus 1. Epsilon B and epsilon B prime are equal to plus or minus 1. And when I make the product of the two, epsilon A B or epsilon A prime B, etc., I will get either 1 or minus 1, depending upon the kind of result they got. Okay, so up to now, it seems very simple. Then Bell had the following idea. He said, let's build the following quantity. I take epsilon A minus epsilon A prime here, and epsilon A plus epsilon A prime here. And I multiply this term by epsilon B and this term by epsilon B prime. And I get a sum here. What is the value of this sum? Either one of these terms is either epsilon A is equal to epsilon prime. So this is 0 and this is plus or minus 2, or this is plus or minus 2 and this is 0. There is no other possibility. And so if you multiply 0 or 2 by 1 or minus 1, you get again 0 or 2. So the result that this sum is equal to plus 2 or minus 2. If you take any sample of result. And of course, each measurement will give you one of these terms. Now, if you make a huge number of measurements, you will be able to take the average of this sum. And if you take the average of plus and minus 2, the result of the average should be comprised something between plus or minus 2. If you keep adding terms which take the value plus 2 or minus 2, the average would be comprised between minus 2 and plus 2. And so you find that this quantity is comprised between minus 2 and plus 2. This is called the Bell inequality. If there are hidden variables, and if I am able to do a large number of experiments choosing conveniently these angles, I will find a result which has to be bounded by minus 2 or plus 2. But then if you use regular quantum mechanics as we know it, you will find that there are angles, directions for the measurement, which gives the result outside the plus 2 minus 2 bound. And this is what I show on the next slide. So first of all, we have to find out what is the correlation between spin measurements at an angle theta. If you measure the spin along the angle theta, what will be the result of the next measurement? What will be the average you will get for the next measurement? And this is something very simple that we can compute from what I said in the previous lecture. The spin plus along the direction theta is equal to cosine theta over 2 plus sine theta over 2 minus. And so if you remeasure then along the z direction, you find cosine square theta over 2 minus sine square theta over 2. So you find that the expectation value of the spin is measured along Z, the first time will give you cosine theta as an expectation value in the second measurement. So what this means is that if you perform measurements, if Alice perform a measurement in one direction and Bob perform a measurement next in the other direction, the product of their result will be cosine theta on average after a very large number of measurements, because these are expectation values. And so what Bell said, makes the following angle choice, which is shown here. You choose theta AB equal theta B prime A, theta A prime B prime, which choose these three angles equal. And of course, the big angle here will be 3 times this angle. So we will have three angles which will be equal to theta, and another which will be equal to 3 theta. And what will be then the quantum result for the Bell sum? The quantum result for the Bell sum will be 3 times cosine theta minus cosine 3 theta. If you look at the Bell sum the way it was written on the previous slide, you find this. This function of theta is very easy to plot. And what you find is that this curve, and you find that there are values of theta for which this average is larger than 2 or smaller than -2. In fact, it goes up to 2 square root of 2 and goes down to -2 square root of 2. So there are choices of the angle theta for which quantum mechanics violate Bell's inequalities. It means that for these angles, there is no way to assume that the values of the spin were existing before the measurement was done. They could not have been elements of reality. So this was the challenge. Can you do this experiment? In fact, the experiment was done in the beginning of the 1980s by Alain Aspect and colleagues in Paris. And they did the experiment not with spins, but with polarized photons. And you can translate this in the language of photons. And the pairs they were using are due to a cascade. You have an atom which has an excited state, a ground state, an intermediate state. So you can emit either a red photon, which is sigma minus polarized, followed by a blue photon, sigma plus polarized, or the opposite. And in fact, you prepare a superposition of the two possibilities. And in this way, you prepare something which has exactly the structure of a Bell state. And by changing the angle of the polarizers here and there, you choose the 4 set of polarization. So you have to translate a little bit. There is a problem is that for spins, 2 orthogonal spins are opposite in space. And for photons, 2 orthogonal polarization are at right angle. So the angles which were chosen by Aspect were twice smaller than the angle in the spin language, but it's the same. The result is the same. And you see the points here are taken from Aspect's experiment. There are a lot of angles for which the result is outside the +2 -2 interval. So this experiment demonstrates that there are no hidden variables, that non-locality is a fact of quantum physics. And so this vindicates Bohr's view over Einstein. And there have been, since then, a lot of tests. I don't want to enter into the details, but there have been a lot of controversy, a lot of tests trying to close all the loopholes, all the problems which might come as perturbing this very simple experiment. I just insist also on the fact that the polarizers here were switched randomly in order to avoid any possible communication at velocity smaller than the speed of light between the 2 detectors, which could simulate quantum effects. And so Aspect was very careful to change the polarization very fast in a random way so that this criticism could not apply to this experiment. So I will finish now by sketching a little bit what quantum teleportation is about. Quantum teleportation is a procedure which was invented about 30 years ago and which was demonstrated later with two-level systems. And it consists in transmitting a quantum state, pure quantum state, from Alice to Bob at a very large distance by using a pair of entangled particles. So at the beginning of a teleportation, Alice and Bob should share a pair of entangled system in one of the Bell states. For example, the same Bell state I have chosen so far. And the rule of the game is the following. Alice and Bob share, each of them, a particle in the state that I've written here. Alice is given a third qubit, which I will call U. And this qubit is in a superposition of 0 and 1 with arbitrary coefficient alpha and beta. What is very special in this is that neither Alice nor Bob now have to know what are alpha and beta. And in fact, if you remember what I said a few weeks ago, if you are given one qubit in a given state, there is no way you can find with only one qubit in which state it is, because if you start measuring, you will destroy the state very quickly. So this state is unknown, a priori unknown by Alice and Bob. But the task of Alice is to send the information which will allow Bob to reconstruct the state in the other location. So what happens? What does Alice? So Alice has in her possession U and A. So B is to Bob. So what Alice does, she makes a joint measurement on the U plus A system. And she makes a measurement, so she gets a result. U and A it's a four-dimension system, so she will get 1 out of 4 possible results. And depending upon her result, the state that Bob possesses will collapse into 1 out of 4 possible states. Then what will Alice do? Alice will communicate the result of her measurement, which will, since you have 4 possibilities, it will be 2 bits, 0, 1, 0, 0, 1, 1, 1, 0. She will tell Bob, and Bob, knowing that, will know what kind of transformation he should apply to his collapsed system to reconstruct the initial one without knowing it. So I have summarized this, and I will let you, as an exercise, to do all the steps. I will just indicate to you how it works, and all the calculations are done on the next slide. So Alice communicates her result to Bob in the form of a 2-bit sequence, and Bob, depending on this classical information, performs a unitary operation qubit B, which brings it in the desired state. So I just give you the steps here. This is the pair of particles which is shared by Bob and Alice. And this is an unknown state that you want to teleport. So the first thing you do is that you expand this into four possible combinations. Okay. Once you have done that, then you regroup the terms to make appear Bell state of U plus A. So you can transform a tensor product of U times Bell state of A and B by a superposition of Bell state of U and A tensor state B. And this is what I do. The following. You see here, you introduce now the Bell state of the UA system. And you see that each of these states is a combination of Bell state of U and A. So you take this expression, you put them back in that one, and then you get now what we want. We get now your 3 qubit states as a superposition of the Bell state of the UA system times 4 combinations with coefficient alpha plus beta, alpha minus beta, and so on, of 0, 1, and 1, 0 for Bob. And so the next thing that Alice will be doing is to determine which of these 4 Bell states in which of these 4 Bell states the system will collapse when she makes the measurement. So Alice has to make a measurement which distinguishes these 4 Bell states. And what Alice does is that she applies a quantum gate. So what Alice is doing is that she applies a quantum gate in which the qubit U is the control and her qubit A is the target. And she does a control X gate, that is a control NOT, and this operation will disentangle her system, and she will get exactly the result she wants. There is one complication that she has to apply to U this operation, this unitary operation. And in the end, see what will happen if the system is in this Bell state. After all this operation, you will find 0, 0, or 1, 0, depending on whether it has sign plus or minus. And if you are in the 2 other Bell states, you will find 0, 1, or 1, 1, once you have applied the gate plus this unitary operation. So I let you do that as an exercise. It's not difficult. In the end, Alice gets, as I said, 2 bits of information. And depending upon which bit she gets, she knows exactly, Bob will know exactly what he has to do. So I summarize this here. You see that in teleportation, you have 2 channels. You have the quantum channel, which is the sharing of the Bell state. And you have a classical channel in which Alice communicates to Bob 0, 0, 1, 0, 0, 1, or 1, 1. And you see immediately that if she finds 0, 0, the system has collapsed here. So then she says, when she says that to Bob, Bob has nothing to do because this is a state that we want. If it collapses into this state, Bob has to make a transformation to get this state into that one, and so on. And Bob knows exactly what are the 4 operations he has to do to bring the system back to alpha 0 plus beta 1. And I summarize this here. You see what this is the recipe, what Bob has to do. He has to apply 4 very simple unitary transformation. And now, in all cases, in the end, Bob's end up with alpha 0 plus beta 1. And you see, neither Alice nor Bob have to know what is alpha and what is beta. They know that if the procedure went well, the state has been transferred. So now I just conclude by the properties of this teleportation process. First of all, so neither Alice nor Bob have to know the state which has been teleported. Second, very important point, teleportation destroys the initial state because Alice is manipulating U plus A, and so the initial state has disappeared. And this is consistent with quantum physics because if the initial state was still there, you would have a copy and you have cloned. If you keep the first state and you have a copy at Bob's end, you have duplicated the quantum state, which is impossible. So this respects the no cloning theorem. Third point, there has been no transfer of information faster than light, because as long as Alice does not send the 2 classical bits, Bob can do nothing. Bob does not know which transformation to apply. So in spite of the fact that there is a collapse, instantaneous collapse of the wave function, there is no information transferred because it's random. The only way to do something useful, that is to transfer information, is to get the 2 bits, which cannot go faster than light. You need an electromagnetic signal to send these 2 bits from Alice to Bob. So there is no contradiction with causality. And in fact, Einstein had understood that. Einstein never said that quantum physics was wrong because it violated causality. He said it was wrong because it violated his idea of what reality should be. Next idea. There is also something very interesting that you have a lot of information, alpha 0 plus beta 1. Alpha and beta can be any complex number such that alpha square plus beta square is equal to 1. If suppose that classically what you would do, suppose that Alice knows the value of alpha and beta, 2 bits will not be enough to transfer the information. You would need much more bits depending upon the precision with which you want to transfer alpha and beta. Here with teleportation, you can transfer any couple of complex number alpha and beta with only 2 bits because you have this quantum channel on top of that. And last point, teleportation is of course something which is also very useful in all the procedure of quantum information, because you see, if you imagine that you have a quantum computer made of a lot of bits, you would like to transfer information from one part of the machine to another part, or from 2 subsets of the computer, and for that, the procedure of teleportation is very useful. But I want to just summarize the difference. Of course, the analog would be a fax machine. Classically, when you have a fax machine, what do? You have a text, you make and you transfer it at a distance on a blank sheet. Here, the blank sheet is the qubit of Bob. It is on Bob's qubit that the state will be transferred. But contrary to a classical fax, you destroy the original. So people are often thinking about teleportation in the context of science fiction as a procedure to transfer someone from one point to another one. It's not at all the case. You don't transfer, you transfer the quantum information on a blank sheet, but you destroy the original. So nobody, I think, would like to be teleported, because if it does not work well, everything is lost. If you lose the original because something has not worked in the teleportation process, everybody is dead. You have lost all information. So it's a very subtle procedure, but it has to be understood. It's quite different from a classical fax machine. Okay. And I will talk again about teleportation in the last lecture when I will describe the physical system like trapped ions or photons in cavities, which can implement this kind of quantum gates. And I will tell you about the experiments which have been done in this field. So I will conclude this lecture. This ends about the first half of my series of lectures, since we have 15 of them. During the first lectures, what I have done, I have mainly talked about historical points about the light. In lectures 4 to 7, I have introduced the principle and main features of quantum physics. And I remind you that all this science has started by general consideration about some mysterious properties of light. And it has disclosed to us a microscopic world of atoms and photons. So it has really disclosed a huge world of systems, of particles, of quantum systems, which evolve in a very big Hilbert space with very, very strange and very powerful properties. So what I will do in the next lecture, I will describe several applications in the domain of electromagnetism and optics, which have been made possible by the knowledge of the quantum laws. I will talk about magnetic resonance, about optical pumping, about the maser and the laser, about atomic clocks and other things. So these are the inventions which have changed our lives during the 20th century. And I will insist upon the fact that these technological advances have been made possible only by the knowledge of quantum laws. And they have also made possible fundamental experiments in basic science. I will talk about very high resolution spectroscopy of atoms and molecules. I will talk about physics of ultra short and ultra intense light pulses, and investigation of extremely low temperature phenomena leading to Bose-Einstein condensation, for instance. And the final note I would like to stress is that it's very difficult in this field of physics to distinguish between what is fundamental and what is applied. And there is a symbiosis between the two. The application comes from the fundamental knowledge, and with the technology which is developed, it is possible to go beyond the knowledge and to discover new fundamental things because of the development, for instance, of the laser. So there is a kind of virtuous circle between fundamental physics application and then using this application back to the fundamental physics. And I want you to remember that and to have in mind that it's artificial to separate basic science from applied science. Usually when think of basic science are being just curiosity driven and applied science being socially motivated, but in fact you cannot separate the two, and you cannot do applied science without basic science and reciprocity. So we'll stop here, and the next lecture will be next Thursday at the same time. Thank you very much.